discussing PN junction diode, which is possibly the most, I guess, the easiest possible device that you can make with semiconductors. Okay, but obviously we discussed why this is still interesting and important, because any device that you can ever encounter will have PN junctions in them. So understanding the properties of PN junction will help you understand the other devices. You cannot just jump into a complicated device and try to understand it. So moving forward, we discussed the concept of metallurgical junction. Second. Oh. Sorry, give me a second. Yeah. So we discussed the concept of metallurgical junction. We discussed, let me move to the other slide. You know what happened? My Apple Pencil, I just realized that the tip of the pencil is missing. Can you see that? I don't know where it went. I'll have to figure it out. Anyways, we can still manage with just. Just bear with me for a second. Okay. So we discussed the concept of metallurgical junction. We also discussed the concept of space charge region. How many of you remember, what happens when you bring P and N-type materials together in a PN junction? Quick recap. Holes from the P-type tries to diffuse to N-type. Electrons from N-type tries to diffuse to P-type. Who stops them? Quickly. Diffusion force will encourage them to keep going forever. As long as you spend all the electrons in the N-type and send it over to P-type, and vice versa. But that will not happen. Because of what? Because when the electrons move over from N-type to P-type and the holes move over from P-type to N-type, because of the separation of charges, positive and negative charges, there will be an internal electric field, right? That electric field will actually act against the diffusion force. And at some point, this electric field will balance. Initially, that electric field will be weak because you'll have small amount of charge. So the diffusion force will win. So there will be more and more diffusion. But at some point, this electric field will perfectly balance the diffusion force, and then they will stop. Otherwise, the moment you connect N and P-type material together, they will just diffuse and make everything N and P. Like no distinct N-type or P-type will be left. Do you see that? Does that make sense? So only within a, yes. Thank you. If you don't mind, I appreciate that. Let's try. Perfect. I hope it works now. Thank you so much. You're a lifesaver. So anyways, it must be in my bag somewhere. Anyways, so where were we? Yeah, we were discussing counterbalancing electric field force and diffusion force, right? Remember, this is the basic of not just PN junction for any semiconductor device ever. You know why? Because in any semiconductor device, you will have P and N-type materials side by side. If I may ask, okay, why always P and N-type material side by side? Why not P and P-type? Why not N and N-type? The quick answer should be, if you have two P-type side by side, it's essentially one P-type. It's not even a device, right? N and N-type is essentially a N-type material. So when the term device comes, it has to represent interaction between different kinds of semiconductors. And obviously, you can have P-type and N-type, P plus N, P plus N plus. That means different kinds of doped semiconductors side by side. Whenever there is an interface, something interesting will happen, right? If it could be between two, it could be between three, it could be between multiple junctions. So more complicated devices will have more interactions, but there will always be interaction between P and N type. You see that? So this concept that I'm reiterating again, diffusion and electric field balancing each other, will be applicable for any device ever. So make sure that this is clear in your mind. So the first thing that happens when you make a device is this diffusion and electric field balancing each other and settling down at a stage. So this zone is the most important, possibly or arguably, most important zone within the diode structure. It's called the space charge region, which determines a lot of factors. So we'll spend some time discussing what happens to the electric field inside that zone, what happens to the potential inside that zone, what happens to the carriers inside that zone, what happens to the Fermi level inside that zone. It's not me, it's just the textbook. It's not me deciding to focus on this. The textbook will spend pages discussing the space charge region itself. Am I making sense? So, all right. So let's move on to the next one. We discussed how to draw the band diagram for a PN junction, right? Just as an exercise, I wish I could give you this exercise and let you work on it. But for the interest of time, I'm going to do it. But please try to work with me on this. Let's do it together, okay? Please. So imagine you have a P-type material and N-type material. P-type, the Fermi level should be close to the valence band. This is the conduction band. And N-type material, Fermi level should be close to the conduction band. Quick questions. Why do you think these two distances will be the same? What is that distance? Difference between the conduction and valence band? Band gap. Thank you. You guys are still silent, okay? Band gap! You should all shout. Anyways, so band gap. This is silicon. As long as you're dealing with the same material, the band gap is a signature of that material. Remember, there will be heterojunction devices at some point, and the name tells you there will be different types of materials, N-type silicon, P-type germanium. Imagine that, right? Then this concept will no longer work. There is a chapter on heterojunction devices, by the way, and I think I'll cover it a little bit in this course as well. So hopefully, if you understand this well, you'll see the difference. Oh, that's what changed. And just by changing this, from all silicon to multiple types of materials, you can have more exotic devices. More about that later. But as of now, it's all silicon, so this band gap should be exactly the same. All right, now, when you bring this together, the first thing that you should care about is flattening the Fermi level. The Fermi level should be flat at thermal equilibrium, obviously. That means you haven't applied any external voltage, remember that. So Fermi level should be flat across the stack, N and P. Now, I'm going to draw the N-type and P-type bands now. First, say the P-type. This is the valence band. This is the conduction band. How do I know? Quick questions. I think I covered all of this, but still, how do I know how much distance to keep between this Fermi level and the valence band, the P-type material? Who can tell me? Can anybody tell me? This is just the separation. How do I decide on this separation? We had an equation a few lectures back that discussed, the number of, so that connected the separation between Fermi level and the valence band with the doping concentration. Remember, we discussed that if you dope it heavier, this Fermi level will move closer to the valence band. If you dope it so heavily that the dopants start interacting with each other, then what happens? Fermi level goes inside the valence band. Remember, degenerate, non-degenerate doping. We discussed this. If you don't remember, please review. Especially use the gap, use the break, fall break to review and catch up before the midterm exam. So because these are important. You might think that you understand it, but when you actually try testing yourself, you realize, oh, I didn't really get it. Okay, so I want you to do that. Anyways, so this is kind of, it's possible to calculate it, right? And then once you figure out the position of the valence band, the conduction band is given. Why? Because EG is fixed. All right. So when I was a student, we were asked to draw this at scale, like not just sketching. We had to draw it at scale. So we had to calculate this first and then draw it and then draw the other one. Okay, next, how do I draw the N-type material? I start with the conduction band. because I can easily understand the separation between the Fermi level and conduction band, because that is determined by the doping concentration. Okay. And then once I calculate EC, I can easily calculate EB, because that's determined by the band gap, right? And I told you to just memorize one thing for a while. That is, at the interface, you just gradually make it nice and smooth and connect them together. I will tell you more about why that is, this way, hopefully in this lecture. Okay. Do you remember everything now? This is all in thermal equilibrium. And by the way, there is a barrier sitting here. Imagine the electrons in the conduction band, when they try to get to the other side, the p-type material, they will encounter a barrier, a potential barrier built into the p-n junction. So that's what the name, built-in potential. Okay. So that built-in potential was this one. And I just gave you this equation. I told you that the built-in potential depends on the doping concentration, the concentration of acceptor and donor, as well as the intrinsic carrier concentration of the material. So for silicon, there is a band gap. For germanium, there is a different band gap. So you have started working with diodes already. Do you know that there is a turn-on voltage for diode? Minimum. For silicon, it's around 0.7, right? For other materials, it will be different. Why is it always that number? Okay, there are reasons. One of the factors is that intrinsic carrier concentration has a big role to play. Okay. So if you move from silicon to germanium, you immediately reduce or basically change the turn-on voltage. Oftentimes, if you need lower turn-on voltage diode, you dramatically change the material. Okay. Anyways, let's move to so this is the built-in potential. Remember that. Now, we even looked at the math problem where you just have to plug in numbers and calculate VBI. So this is where we start with the really new part. There was a big gap, so I decided to just, quickly review it. Now, we're going to do some simple maths, and honestly, it's not going to be that difficult, very quickly, to make a couple of points. How do you calculate the electric field inside the space charge region of a diode? And how do you calculate the potential or voltage, whatever you want to call it? Typically, we call it potential, okay? A potential within that region. And you will hopefully easily understand why it is important to figure these things out. So let's start with this simple diagram that we saw before. This is the space charge region, remember that. And we take the metallurgical junction. See, I'm using jargons now because I've explained this before. The interface where the p and n-type material meet each other, that's called metallurgical junction. Right? When you go to semiconductor industry, they'll just use it like coffee. Oh, are you going to have a latte? What is a latte? I don't know. If you don't know a latte, what do you do, right? So it's understood that you know what a cappuccino is or a latte is. Maybe, for example, when I came to the US, I didn't know what a cappuccino is actually, because in that part of the world, we just drink tea. There's coffee, but people don't typically, drink that much coffee. Anyways, tangent. But the point is, if you want to get into the gang, you need to understand the jargon. Okay. So now I do. I know all sorts of coffee. The point is, I hope that by the end of this course, you will be super comfortable with all these jargons. I'm going to just tell you, hey, so, what's going on at the metallurgical junction? And you will understand what I mean by that. What's going on in the space charge region? So this is the space charge region. There is an end point of the space charge region in the P region and in the N region. So you have to mark it. So let's define the metallurgical junction as our point of reference, 0. That's where our origin is, for example, right? And towards the right side, we define the end point as xn. And towards the left, we define it as xp. Since it is on the left side of the origin, we are going to define it as negative xp. This is standard, by the way. That's why I'm spending time. Xn and xp. These are almost like parameters, given parameters. Xn represents the width of space charge region in the N side, and xp represents width of the space charge region in the P side. Now, if I ask you, what is the total width of the space charge region? You should say xn plus xp. That's the width of the space charge region. Okay, super simple. It's like a geometry class. All right, now, I mean, I feel like when I was a student, when my professors used to discuss this simple stuff, A plus B equals C, come on, man, what is the big deal? I didn't realize it then. So I try to go ahead of myself and tell you some context. Solar cell design, basically, a big part of solar cell design deals with optimizing the space charge region. I mean, if I told you that the solar cell efficiency, will it be 15% or 20% or 22%? Depends on the efficient design. I'm saying because you can control the space charge region, by the way. Figuring out how to best control the space charge region, that determines your efficiency. Would you now be interested? Right? And this xn plus xp, this simple line, will actually help you design. You have to reduce one of them and increase the other one. Now you see. Okay, the simple equation leads to an entire direction in research, solar cell optimization. And don't worry, we'll discuss that in this lecture. It's not like, okay, at some point you'll learn. No, in this lecture, and I'll show you how. So please pay attention. Now, let's move here. In this region, we had negative charges. In this region, we have positive charges. Who can tell me what is the origin of these negative charges? Are these the electrons? Are these the electrons? So what did you have in the P region? Let's start from there. What did you have in the P region? You had holes that are positive charges, right? H plus, H plus, H plus everywhere. What happened to them? When you connected the N-type material, they diffused to the other side. So what did they leave behind? We talked about it in the last class. What did they leave behind? So holes came from what? Came from the dopants. Basically, dopants led to holes, and dopants led to additional electrons, right? Remember I told you this? So the holes were, when the holes leave, they leave behind fixed charges. Like, for example, in a silicon, 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 silicon. Imagine in this situation, there is no free electron or no free holes. But if you had, say, a trivalent atom or a pentavalent atom, for example, if you have arsenic, say you have arsenic, you have 4 bonds and then you have extra electron, right? Let's discuss in terms of electrons because holes are confusing because you know that they don't exist, right? They're just a dummy concept. So electrons are easy to explain. So arsenic has an extra electron. Do you think this arsenic is a charge here? No, it's just an element. It's just an atom. It's not charged yet. It has 5 electrons. It just cares less about one of them and cares more about the other 4. So that one electron that is less cared for leaves the structure and moves away. As long as, remember, as long as you just had p-type material or n-type material, just n-type or just p-type, the electron is still within that material somewhere. Yeah, I'm here. Don't worry, I'm still here, right? So essentially, even when this electron is gone somewhere else, it's still there in the structure. So when you give up an electron, you become positively charged, but the electron is negatively charged. But they balance each other. Essentially, you have 0 charge. Does that make sense? You're charge neutral. But what happens in a p-n junction? That electron that you gave up can move away from the n-type all the way to the other side. Like it's gone now. So that n side all on a sudden starts saying, hey, where did my electron go? I no longer have that electron that could screen my charge. So now I am a positive charge. Does that make sense? So the dopants who led to extra electrons and extra holes, they are essentially charged. But you don't really represent them as charges because the electrons and holes are always there to screen them out. It's not like we are there, you're not really a charge. But then when the electrons are diffusing to the other side and holes are diffusing to the other side, they're essentially leaving the picture. And you have these regions that are essentially charged dopant. We discussed this. Please review the last lecture as well. I think I talked about it as well there. Okay. Are you guys all with me so far? So what is special about these charges then? versus the electron charge and hole charge. Because electron charges can move from one place to the other. Holes can move from one place to the other. So they will never be in one place. But these charges are fixed. As you see, they're basically tied with 4 bonds. And then they are positive charge or negative charge. So they're essentially stuck. So you have a very stable charge shift. Positive charge shift, negative charge shift, basically side by side. Like a parallel plate capacitor. Does that make sense to you guys? All right. Now let's see. Let's see. If I try to draw the charge density, and I can start with, just take a look at it. This is negative charge. This is positive charge. Okay. And the charge density, maybe I can draw it here. It's probably less confusing that way. I'm drawing charge density versus the direction. So this is my metallurgical junction. So this is origin 0. Here I have Xn. And here I have negative XP. You see what I'm trying to get at? I'm trying to draw these 2 positions, Xn and XP. Okay. So imagine that your doping concentration in this region was ND. D stands for donor concentration. And here it was Na, acceptor concentration. So let's consider you have donor concentration ND. Right? If the donor concentration is ND, what is the charge? So you have ND amount of charge, but each of them has the charge equal to the charge of an electron. So what is the total charge? Imagine you have 10 donors. What is the total charge? Tell me. 10 donors. 10 charge of electron. Yes, thank you. 10E. So similarly, if you have ND charges, you have END. That's the total charge. Does that make sense? So that's what I'm going to draw. END is the total charge up to what point? And we are assuming uniform doping. It's like uniform everywhere. So I can just draw that the doping concentration is fixed up to this point. See, up to the space charge region. After that, it's again balanced, by the way. It's still n-type, so it's balanced. Only within this region, you remember, the electrons in this region migrated to the other side and they're gone. Holes in this region migrated to the other side and they're gone. So they left behind the ionized dopants. And now they're fighting with each other, right? These dopants are fighting with each other by creating an electric field. Okay. So does that make sense to you guys? So up to Xn, there is a charge density coming from the dopant. And this is positive charge. And for the other side, p-type, it's negative charge. So we are going to draw it on the other side, negative y-axis. And what is the concentration? Using the same argument. Na is the number of acceptor atoms. So you should have ENA as total charge. And up to what point? Up to XP. Does that all make sense to you guys? Okay. So that's where this comes in. And this is a very popular exam question, by the way. Even it was an exam question, I took the exam. And even in many interviews, they ask you to draw the charge density, not just for diodes, by the way. There will be space charge region in any device. They'll ask you to draw the space charge density in a BJT or a MOSFET. So if you understand and do it here, you'll be able to do it there as well. Right? So I hope that makes sense. Super simple. All right. Now, let's move to the other side. Let's talk about electric field. And by the way, Gauss's equation, which I don't want to get into too much math, but still, very quickly, derivative of electric field. And when I say derivative, space derivative. So there are 3 directions. Electric field equals charge density over epsilon. Okay, that's Gauss's law. So that's what you see here. Derivative of electric field is charge density over epsilon. Epsilon s, whatever you want to use, doesn't matter. Okay. So notice that in this region, in this section, there are 2 negative signs. So they will basically cancel each other out. So don't worry about the negative sign here. I'll tell you where the negative sign comes in from. But this is essentially Gauss's law. And since we are simplifying the problem, we are not considering 3 dimension. We are just looking at one x direction, just to make our life easy. We're going to ignore the other 2. But remember, in real calculation, we'll do all this. Okay. Okay. Now, so essentially, you have d dx rho over epsilon s. And rho is a function of position. Rho is a function of x, by the way. At different position, it's different. How do you know? Along x-axis, you can have some value or you can have 0, you see? So it changes with position, right? Or if you go to negative x, it changes again. So rho is a function of x. That's what this represents. Now, I'm going to express rho is x, simple equation. Can I write that rho x, let me just use this one first. Rho x is equals E and D up to this range. Notice this range, starting from 0 all the way to xn. That's the range. Can I write that? Folks, don't give up. Math will be over soon. Trust me. Please don't give up, okay? We're going to see that, light at the end of the tunnel, honestly. And there is no way I could skip this much math, honestly, because this is essential. Why, you might ask? If you ever go to interview for any semiconductor industry, they will ask about Gauss's law. And they will ask to see whether you know how you arrive at this situation from Gauss's law. It is a very popular, I skipped a lot of maths, by the way. For example, I didn't bother you with this, origin of this equation. I could derive it with the stuff that I covered already in the previous class. But I just told you, okay, it's fine. Just based on NA and ND, you can calculate the built-in potential. But this is a very popular question, okay? So, are you okay so far? All right. And this is super simple, by the way. So, rho x is nothing but E and D up to a range, 0 to xn. So, that's what this equation tells you. And what does the other line tell you? This is defining the other section, starting from 0 to negative xp. Rho x would be negative En. Simple. So it's just defining. It's like piecewise linear function. You see that? It's a piecewise linear function. And everywhere else, rho x is what? Everywhere else, here and there, rho x is what? 0. All right? So you know that now. Okay. So keeping that in mind, I'm going to now do the math here. So dE over dx. How can I calculate the electric field? Sorry, I meant to just calculate E. Electric field would be rho x over Es or dx integration, right? And the integration should be from where to where? Negative infinity to positive infinity. Imagine. But beyond xn and xp, just visualize it. I don't want to go back again. Xn and xp, it's what? Rho x is always what? Beyond xn and xp, it's always what? 0. So I can write from negative infinity to negative xp, rho x is 0. So basically, we don't care. And then from negative xp to positive xp, we have rho x value. So you should care. And then again, from xn to positive infinity, rho x is again 0. So we don't care about these two cases, right? They're gone. Are you still with me? Is it visible or no? So all I'm saying is below negative xp and above positive xn, rho x is 0. So the integration will be gone anyways. The only limit that you should care about is from negative xp to positive xn. So that's what I'm saying. So essentially, let's get rid of all this. I should just change my integration limit from negative xp to positive xn. That will suffice. And even then, I should divide it up into two parts. I should start looking from negative xp to 0, because you see, negative xp to 0, up to this point, I have a special value for rho x, which is this. And for the other part, I have a different value for rho x. Okay, so I should do this integration in two parts. Does that make sense to you all? All right. So if you then do that integration, which is super simple, maybe this could be a homework to go through the steps. And actually, I have homework 3 where it doesn't matter. Even if you don't do it, it's fine. But it will hopefully give you more clarity as to, oh, this is how it happens. Fine. So if you go through the math and do the integration, actually, you end up with two expressions for electric field. One for this region, the other one for the other region. You might be wondering, why do we have two expressions for electric field? I hope now you understand because you have to do this integration in steps. In one step, you do this, the other step, you do the other one. It's piecewise linear. Okay, so just through pure integration, no other fancy physics here, pure math, you end up with electric field is this, and for the other one, electric field is this. And you see there are ranges. And you plot it like what you plot y versus x, right? Just plot it. Maybe if you plot it in MATLAB, you get a graph like this. Super simple. And you can easily also relate it to how things look like. For example, you know, y equals mx plus c is the equation of a straight line. If whatever you have with x is positive, you have a positive slope. Say, for example, y equals 2x plus 3. That's a positive slope. If you have y equals minus 4x plus 7, that's a negative slope, right? You can easily understand that. So look at this one. It is essentially a negative slope. You know why? Because there is a negative, you know, some sort of constant in front of it. So it's a negative slope, right? But for the other one, there is a negative sign in front of x and another negative sign here. So they will essentially become positive. So you have a positive slope line. There are different ways of looking at it, but it doesn't matter. You could just plot this one and the other one, you get these two equations. Does that make sense to you all? So you see, within the space charge region, electric field is not really constant, is it? It's not constant, is it? I mean, when I discussed it, it was like, okay, there is an electric field. Fine, sure. It felt like there is one constant value of electric field, which is not true. It is a more complicated situation there. Are you guys okay with it so far? Okay. Now, let's see. Using these two equations, we will arrive at a very important equation here. Are you guys ready for it? At this point, both equations should meet. This is called a boundary condition, because at the boundary, you just have one solution. You cannot have two different electric field at the same point, right? So what is that point? Can anybody tell me? What is that point? X equals 0. So I'm going to put in x equals 0 in both equations. And I'm going to equate the electric fields because they should be equal. Are you good? And in doing so, you end up with this equation. Na xp equals ndxn. Just set it aside for now. Like, okay, this is an equation, super simple equation. And trust me, from these super simple equations, a lot of usefulness will come up eventually. Are you guys all good so far? Okay, so just notice what is it relating? It is relating the acceptor concentration with the space charge region in the p-type layer and the donor concentration with the space charge region in the in layer. Okay, so just keep that in mind. We'll revisit this. Let's mark it as equation 1 for the time being, and I'll get back to this slide later on. Now, so that's the electric field. If I ask you to draw the electric field in a p-n junction, I should start from this 0 and go to xn, go to negative xn. Negative xp. Okay, and then this is how your electric field should look like. Are you all good? All right. Now, if I ask you to find the value of this point, how can you do it? Super easy. Just put in x equals 0. You get something ENA XP ES. Or you put in x equals 0 here. Basically, they're the same, by the way. NA XP equals NDXN. Doesn't matter. So E ND XN epsilon. That's the electric field value here at this point. Simple. So you can calculate it. Why am I showing you this? I'm telling you, there will be a question in midterm exam to calculate this maximum electric field. Now you pay attention. Okay, let me see. Anyways, all right. Let's start looking beyond the exams, by the way. I mean, that's exactly my vision for teaching, honestly. I want you to pay less and less attention to, you know, the points and grades. Obviously, I want you to get good grades. So don't get me wrong. But honestly, this is a given. This will not really change much in your life. In real life, let me add a real life perspective here. How many of you heard about microelectronics reliability? Have you heard the term reliability? And we always use it. How reliable is your system, right? It means something, and we know what it means. The name suggests what it means. So reliability for microelectronics is a concept that determines what happens to a device, not when you start using it, but after repeated usage. Okay. So imagine, so all companies have a warranty policy, 1 year, 3 year, 5 years, right? They determine a warranty based on their expected reliability. They know that our system is not going to break down in a year or 2 years, but it might break down in 3 years. But we are never going to extend that warranty beyond 3 years, because otherwise we'll get all returns and we'll be bankrupt. Making sense? And by the way, if you get a reputation that your devices break down after 2 years, nobody's going to buy them eventually, right? So you have to make sure there is a higher reliability. So people can, all these big companies, all of these big players in the market, they have reliability teams that all they do, and this is a really nice way to put it, they break down things. So they just try to make them fail. That's all. You know, how many of you, I don't know if you have seen that product video from Apple or some other companies. So there are some phones that fold, right? From Samsung. There was a video. They showed that we tested it that many thousand times, literally a machine folding and unfolding it. There is a video, by the way. So they tested it, I don't know how many thousands of times to make sure it works. So it's a reliability at a higher level, at the system level, like literally mechanical reliability. But something similar happens at very lower level, at the transistor. You have billions of transistors. You just test one transistor and you test it like billion times. You make it switch over and over again and see when it breaks. Why am I telling you this all on a sudden? One of the factors that make electronic devices break down. What do I mean by breakdown? You know, lightning is nothing but a breakdown event. Breakdown of what? Breakdown of oxide. Air is an insulator. Sorry, breakdown of an insulator. I meant to say insulator. Okay. Air is an insulator. It's supposed to not let any electric current flow. But during lightning, you have a current flowing through the ground, right? So apparently insulator failed to work. So it broke down, right? With high, see, when do you have lightning? Whenever there is a high voltage buildup, voltage difference buildup, that's when you have a lightning. So electric field is directly related to voltage. Higher electric field represents higher voltage. Okay. So whenever you have a high electric field buildup, there is a higher chances of breaking down. Air is an insulator. So is different oxides. So in semiconductor devices, you have a bunch of oxides everywhere. They have specific purpose that they play a role in. So apparently, these electric fields help you identify the breakdown potential. So basically the likelihood of breakdown. Am I making sense? So just by calculating this, you can understand whether this will be reliable enough or not. So now that's the real life perspective, but also there will be a midterm question on this. So whichever you care about, doesn't matter. But it's a very simple concept. Like you basically just derive these two equations, put in x equals 0 and calculate this value, E. And this is negative because it's in the other side, but you don't care about the sign. It's just a convention that we are taking up. Negative or positive is just our convention. It's just the magnitude that you care about, right? Okay, enough maths and sidetracking. Let's go to the next step. You know, electric field is basically a derivative of voltage, negative derivative of voltage, right? These are all from definition. And convention. Sign comes from convention that we agreed on, and definition, basically how we define voltage and electric field, right? So I'm not getting into that. So if you calculate electric field, you can then take another derivative. Are you still with me? So basically, if you calculate electric field, sorry, I mean electric field is dov over dx. I was saying that if you calculate electric field, you could just put it in here and then find out voltage by taking an integral of electric field. Don't you see? So basically, there will be a negative sign getting to the other side, and there will be an integral of the electric field. So whatever equation you derive, just integrate it one more time with respect to x. Now, I hope you guys remember integration of x dx is x squared by 2, right? Like simple. So that's exactly what you're going to end up with. So here you see, if you go through the math, which I will make you do as a homework, that way it's less stressful and you're more relaxed and see, oh, I see. And you do it once and you forget about it. You don't care about it for the rest of your life, honestly. Okay. But you know that, oh, this is how it comes. Okay, so you calculate the electric potential just using the definition, using math. And then you try to make physical sense of the math, not just numbers. You try to make physical sense of the math. Let's do it now. So you have two expressions for electric potential because you had piecewise linear electric field, right? So within this region, negative xp to 0, you draw a portion. And for the other section, from 0 to xn, you draw the other section. And as you know, boundary condition, at this point, they will always be the same value. So they will really nicely match with each other. And you see, both of these are quadratic. So that's why there is a really nice, smooth transition because of the quadratic nature. It's not linear. We're not just going to draw a straight line, are we? You see, there is a square on top of x. Notice that, x squared. Does that make sense? So it's a quadratic dependence, not a linear dependence. So when we connect this xp to xn, we will have to draw it as if it's a quadratic line, not just a straight line, not a straight line. Are you guys all with me so far? You know, voltage or potential and energy are basically the same. We often use potential energy, basically. We use the term this way, right? If you can calculate the potential, which is like voltage, in some places, people just prefer calling it voltage. If you multiply it with the charge of electron, you get energy in electron volt. So if you have 1 volt, you can consider it to be 1 electron volt. Okay? So essentially, you can convert it to electron volt. That's typically the norm in semiconductor industry. Instead of joule, we express it in terms of electron volt. So voltage is basically, potential is proportional to energy. So energy, let me just write it here, is proportional to potential. So it could be just a factor. Instead of, it might go up or down when you change the factor. That's all. But the shape will be exactly the same. Does that make sense? The shape, the curvature will be exactly the same, except for that it might be scaled up or down when you switch from one to the other. Energy to potential, potential to energy. Just factor of electron charge. Multiply or divide. That's all. Move from one to the other. So why am I telling you this now? Remember that situation where I told you, just 1 second. Remember the situation where we drew the Fermi level for p-type, n-type, p-n junction, right? And I told you that we will not do this. We'll not just add it as a straight line. What will you do? You'll make it nice and smooth and connect it this way. You know where that curvature comes from? This is energy, by the way. Energy band diagram. This is energy. Energy curvature will be same as the potential curvature. And the potential curvature, math told us, it's quadratic. It's not linear. Unlike the electric field, which is linear. Electric field is linear, but potential is quadratic. So there you go. That's why you connect. And by the way, notice, where are we making this curvature? This is xp. This is xn. That's where the connection occurs. Exactly at that point. This is the space charge region. In the middle, you have the metallurgical junction. Are you guys with me so far? So there is reason behind drawing everything. Are you all good? Okay, sure. Now, math you can handle, by the way. So from these equations, I'm going to help you find VBI, built-in potential. There is another way to calculate VBI. I showed you this equation, and I didn't, show you the proof or anything, because that came from the previous equations that we studied in the last few lectures. And that showed, if you know the doping concentration and the material intrinsic carrier concentration, you can calculate the built-in potential. That's fine. But there are other ways. There are other factors that you can use to calculate built-in potential, and this equation tells you that. And this is taken from textbook, so I wanted to cover it. Remember, potential is relative to your standard. So you can choose one to be zero potential and calculate the rest with respect to that potential, right? When you write 10 volt is related to a ground, right? When you do circuit analysis, you consider a ground, and with respect to that ground, the other point is 1 volt, 5 volt, 10 volt, right? So there is a reference point. So we have to take a reference. And the standard that people take is they take this point XP as 0 volt. Are you guys still with me so far? That simplifies, doesn't matter, without losing the generality. You could choose other things as well. But that's like the agreed upon standard. We choose this to be 0 volt. And then notice this is basically the potential barrier that you noticed in the PN junction here. Remember, there was this curvature led to the built-in potential. So if you could calculate the height of this curvature, you get the built-in potential. Don't you think? The height of the curvature comes from where? The height of the curvature comes from this potential. The difference between voltage here and here. So if you could calculate this difference, there you go. You have the built-in potential. What is the difference here? If this is 0 volt, whatever voltage you get here, you just take the difference, which is basically the voltage at this point. And that is the built-in potential. So if I replace in this equation, say, if I replace x equals xn, see, that's what it says. If you replace x equals xn in this equation and do some calculation, whatever phi x you get at this point, that's your built-in potential. Did I successfully confuse you with this? Okay, I managed to confuse you again. All right, my point is, I mean, I didn't have to go through this anyways, but it's there in the textbook. If I don't cover it, at some point you'll get confused. So I want to cover it, okay? So the textbook showed you that there is another way to calculate built-in potential using this potential expression that you have just derived, okay? They told you that, oh, by the way, notice that the height of this curvature, this is basically the determining factor for built-in potential. So instead of using NA ND to calculate built-in potential, let's use this equation to calculate it again. Why? Because we can. Let's do. So apparently this is potential as a function of position x. Okay, I understand the potential at this point, which I have taken as 0. I want to calculate the potential at what point? Tell me, at what point? At this point. V, say, so that I could get the difference. And what point is that? X equals xn. You see that? If I replace x equal xn here, then whatever phi x I get, whatever phi x, the potential I get, that is going to be my VBI, built-in potential. And that's exactly what they did. See, built-in potential is nothing but phi at x equals xn. So basically, they're going to replace x equals xn, do some calculation, and end up with an expression. Done. Does that make sense to you guys? No? Why are you so silent? Tell me, what does this equation represent? The potential at what point? At what point? Any point. Why? It is a function of x. If you want to get potential at this point, tell me what is x, say 0.2. Sure, I'm going to put in 0.2 and get the potential. Okay. If you want to find potential here, sure, tell me the value of x, I'll get it from the equation, right? For my purpose, I'm going after the built-in potential, which is basically the potential at this point, because this one is 0 already, right? So I just want to calculate this point. What is the x for that point? Xn. So I'm going to just replace x equals xn, and whatever expression I get, that is going to be my built-in potential. Got it? Okay. So there you go. You have another equation, another expression for VBI. Another expression for VBI, which is interesting. Now, in this slide, and this is again homework thing, solve these two equations. I'm going to give you as a homework later on. Don't worry about the homework for midterm. Maybe after midterm. I don't want to bug you with this. This is only meant to help you brush up on the concept. That's all. Okay, so remember equation 1. Oh, wait, this I meant this to be one of the equations, right? And this is another equation, equation 2. Bring them together. This is one, this is the other. So we have seen these two equations. And I'm giving you the hint, basically. If you express, say, xp equals ndxn over na, just calculate xp here and replace xp in the first equation and do some calculation. It's as if, imagine, xn is alpha, xp is beta. It's like you have two variables. So you have two variables and two equations. Can you not solve for alpha and beta? You can. Just replace from this equation, get alpha and replace it in the first equation and calculate beta. And then there you go. You need two equations to solve two variables. Okay. So apparently we can solve for xn and xp by doing some simple math. By the way, these steps are also given in the textbook, so you could just cheat. When I give you as a homework example, if you're lazy, just follow. But I want you to go through it gives you a different feeling. Once you go through it, once you feel like, okay, I can do it. I'm not going to do it though, but I can do it. But anyways, so xn and xp, you can calculate it. The expressions look complicated. You feel good about it. You feel like you are an engineer or maybe like a mathematician, but doesn't matter. It is what it is. So what we care about as an engineer is how can you change xn and xp? Notice that here. How can, if for some reason, assume I haven't given you the reason already, right? For some reason, you want to change xn, you want to reduce it, or you want to increase it, and vice versa for xp. How can you do it? These equations will tell you how to do it. What are the variables? What are my options? My options are Na and Nd. Doping concentration in the acceptor side or donor doping concentration, right? And what are the other things? Electron charge, epsilon, these are all constant. VBI, by the way, built-in potential, this is a dummy variable because it itself depends on Na and Nd, as you know, right? So it's not really a variable. So notice how powerful this concept of doping is. It even allows you to, by modulating the doping concentration, you can change this. You can redesign or engineer it at will. Okay, keep that in mind. And that's true for both xn and xp. One other thing, if I ask you, what is the total space charge width? What is the total space charge width? I mean, as I showed you, just add these two equations up. This is also part of the homework. Just add them up, calculate, and you end up with that other equation. Simple. Okay? You don't have to memorize any equations, as you know, right? All of these will be given. So for all practical purposes, you are covered. You're insured. So it's not a big deal. Now, using that argument, let's do some quick math. Consider a silicon p-n junction. The reason why we hint at silicon, because we want you to plug in number for silicon from the table. Oh, what is Ni for silicon? Oh, okay, that much. At T equals 300 Kelvin, with doping concentration, Na equals something, Nd equals something. Calculate the space charge width and the peak electric field at the metallurgical junction. You see, we have started using more and more jargons in the math, right? Okay. All right. So what is peak electric field at the metallurgical junction? Let me show you again. Just, okay, no, I don't want to draw it again. What is the metallurgical junction? This is the metallurgical junction. Remember, x equals 0. What is the peak electric field? This was the peak. Didn't we calculate it before? Did we? Just put in x equals 0 in any of these equations. And you have E equals ENT xn over ES. Simple. Okay? We'll get there. Now, first we want to calculate the space charge width, which is given by this equation. And you know Na, Nd. You don't know VBI, but you can calculate VBI as well using Na and Nd. So you have all the information you need. You can calculate the space charge width. And for this peak electric field, which is Emax, peak electric field, maximum electric field, Nd is given you need xn. How can you calculate xn? Just in the previous slide, we saw we have equations for xn, xp, as well as w. Whatever you need, just plug in the numbers. So using these equations is super simple. Did I tell you, I think at the very beginning of the course, that you can choose your poison. You can decide to be as involved in maths and physics as you want, or you could be as checked out as you want. I don't care, man. I mean, this is too much for me. I don't want to deal with, Gauss's law, continuity equation. Fine, sure. Just be a user, right? Like, for example, okay, just take these three equations, make devices. Fine. Just play with doping concentration. As long as you understand that, you are good. I mean, work at a higher level. You don't necessarily need to go deeper into the weeds. Making sense? All I want to ensure that you guys don't give up, because there has been generations of students giving up for no reason, because it was presented to them in a way that it's like super complicated. If you're not like Sheldon Cooper, I hope you know who Sheldon Cooper is. Like, you have no chance at, it's not for you. Anyways. Okay, so let's move to the next one. One-sided p-n junction. What does that even mean? Hopefully things will start making more sense gradually. How many of you remember what p plus and n plus represent? Heavily doped. If you have an n-type material, EC, EV, if you heavily dope with n plus, the Fermi level could be inside the conduction band. Or basically, to simplify the stuff, many textbooks, rather than showing it inside the conduction band, they just show it at the conduction band. It's all the same. Basically, you are already at the conduction band. So all the electrons at the Fermi level are available to conduct. Doesn't matter whether you're here, 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 here. Basically, you have crossed the, if there is a finish line, right? If you touch the finish line, your race is over. I mean, if you touch it and go inside, does it matter? Doesn't matter. Like, you can go inside, or you can just touch it and stop there. Doesn't matter. So that's why in many textbooks you will see EC equals EF, EV. That's n plus. Sometimes they write it this way. So don't get confused. Okay, it's all the same. Even if I write the Fermi level, draw the Fermi level here, it's basically the same. Okay, now moving back to this one. What is a one-sided p-n junction? Look at this one. Does that figure look familiar to you guys? Did you see a similar figure today, earlier in the class? Where? Here. Space charge density distribution. I told you that in the P region, you have ENA, in the N region, you have END, and blah, 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 right? And starting from this figure, we decided on the limits of integration and calculated electric field. And then from there, we calculated potential. So that's where everything begins, from that charge distribution figure. So now we are looking at a different charge distribution figure where things look a little bit strange. See, you have a huge, spike in charge in one side, and in the other, it's thicker. So you have a thicker space charge region in one zone, and you have a thinner, really thin space charge region in the other zone. Does that make sense to you guys? Folks? Okay. I'll explain how to get it. Let's just do it using math first, and then I'll give you the physical reasoning. Okay? Because I think having exposure to both makes a lot of sense. Just look at xn and xp. What happens when Na is far, far, far greater than Nd? Like, I use heavy doping in the acceptor side and not so much heavy doping in the donor side. Are you guys all with me so far? So I'm assuming Na is far, far greater than Nd. So let's do some math here. So when you say, imagine you have 1000 plus 0.1, can you just consider it to be 1000? I just ignore the other one. Similarly, you could just ignore Nd because it's so small compared to Na, and just keep Na. Okay? And then you can do some math, and there will be some interactions with this Na and the other Na. Oh, I haven't written the equations because this is also a homework problem. I want you to put in these numbers and calculate what happens to these equations. Okay? So apparently, just when you ignore one of them, maybe ND is gone, then this Na will interact with the other Na. And apparently, you can see the zone where you have heavily doped. You can calculate the numbers. The zone where you have heavily doped will have a really small space charge region. So if you heavily dope the P region, are you hearing me? If you heavily dope the P region, the space charge zone in that region will be thinner, and the other one will be thicker. So whatever you heavily dope, it will have a thinner space charge region, and the other one will have a thicker region. So long story short, how can I create a one-sided junction as if there is no space charge in one side and a lot of space charge region in the other side? So I'm just skewing it. Instead of putting it equal in both sides, I'm making one of the sides skewed, super narrow, and the other one wider. Okay, how can I do it? By heavily doping one side. Whichever you want to make narrow, heavily dope it. When you heavily dope it, it will basically make the space charge region narrow in that zone. And that's exactly what's happening here. In the P region, you have a really narrow, because it's P plus. Notice it's P plus, heavily doped. And on the other side, it's thicker. I'll explain the physical reason now. Are you guys all with me so far? And you can see from math, just put in the numbers. Oftentimes, you can be agnostic to physics and just do the math, and the math will tell you this is the result. And by the way, that's what happened a lot to many of the leading scientists like Einstein. So he did a lot of math, and the math led to crazy conclusion. Like, oh, you can convert matter to energy and energy to matter. Well, what? Equals mc squared, right? So the math told him, or told the scientists at the time, it's possible. But who would have believed? Like, can you convert that chair to energy? It's like some sort of magic or something, right? But theoretically, as you know, that's true. Like matter and energy equivalence. Apparently, that ended up being the truth eventually. So math often tells you the hard truth, and you figure it out at some point how to do it. So math told us it's possible to skew it. And now let's try to understand this physically. Right. See, when you have a really heavily, essentially in this diagram or this type of diagram, what you're looking at is charge balance. Remember, charge balance. Here is what it means. You need to have equal amount of positive and negative charges to balance out each other. If you have more positive charge in one side and less in the other, it will keep building up charge on the other side until they are equal. They have to screen out each other perfectly. Are you guys all good with me so far? Okay. Now imagine, I'm looking for empty space. Okay, imagine I'm just drawing metallurgical junction. You have like very lightly doped region. These are all charges, by the way, lightly doped charges. Okay? And these are heavily doped charges, like super heavily. I mean, I'm trying to make it super dense. I don't know if it is doing its purpose, but hopefully it is. Super heavily doped everywhere, like everywhere, super heavily doped. Now imagine if you have 10 positive charges here, you need 10 negative charges to the other side to balance out. When you create space charge region, it's as if uncovering charges, uncovering 10 positive charges here and 10 negative charges to the other side. Okay, so to uncover 10 positive charges, don't you think you need to dig deeper? Because the charges are so sparse and farther out, you have to go deeper to get 10 charges. Do you guys all agree with it or no? So you have to go deeper to get 10 charges. But here, like very close to the surface, you get 10 charges. Do you guys see the reason here? So when you heavily dope something, there is so much charge, you could, like within very close proximity to the metallurgical junction, you get enough charge to balance out whatever you have in the other side. So the other side has a thicker space charge region, and the one that is heavily doped has a thinner space charge region. Does that make sense to you guys? Okay. And also, there is another way to look at it. This is again from math. So basically, the area under this curve should be equal to the area under this curve. Okay. Why? Can anybody tell me? This is a trick question, but I would be surprised, but pleasantly surprised if you can answer that. Why do you think that that is the case? The area under this curve, say area 1, should be equal to area under this curve. What is the area? What does the area represent? We already discussed it. I didn't tell you this, by the way. Remember, electric field is the integration of rho over epsilon dx. Remember? What is integration? So if you have y versus x graph, what is integration y dx? The area under this curve, don't you think? So when you integrate rho dx, you are basically calculating the area under this curve. And when you calculate the rho dx integration on the other side, you're calculating area under this curve. Why should they be equal? Folks, remember, at this point, electric field should be equal, don't you think? So electric field is basically nothing but the area under this curve, the maximum electric field. So you're, by equating area, you are calculating the electric field at this point. So apparently, notice, if, very simple, if I reduce this dimension, right, if I make it narrower, what should happen to the height? What should happen to the height? Or, okay, let's do this the other way. If the height is higher, like if I have more doping concentration here, what should happen to the width here? To keep the area the same, width should reduce to keep the area the same, right? Otherwise, the area will increase. So, you see, if one thing gets, longer, the width will be shorter. So there are different ways to see it. Just by using math or using physical understanding, doesn't matter. So one-sided junction is doable and can be used heavily, and they are used heavily for many purposes. In the next class, we'll start with, see, we have started looking at non-equilibrium here. So we'll start applying bias. So far, we have covered everything in thermal equilibrium. Moving forward, we'll do non-thermal equilibrium. Okay. So have a great fall break. Let me know if you have any questions. I'll see you all after the break.